Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we will discuss about a synchronization tool implemented by a software API known as Monitor. Now first we will know that what are the faults of semaphore that cannot be addressed while solving the critical section problem. After that we will know what is the need for monitor and how a monitor is implemented in different ways. Although semaphore provides an excellent mechanism to provide process synchronization and concurrency problem solving, but it has some limitations too. Like if we inaccurately use these semaphores, it can problem time errors which can only occur if some particular program execution sequence has been executed. Now this sequence does not occur in the operating system all the time, thus it is very difficult to detect this type of error. As we have previously discussed the bounded buffer problem where the counter was giving inaccurate value when the producer and consumer was executed combinedly. But it was reasonable as the counter was only incremented or decremented wrongly by the value 1. But it is not acceptable at all because it is giving in any way an inaccurate value. Thus, in case of semaphore also, with the wait and signal operation, it's sometimes given time error value when it is giving in an inaccurate way. Now, if we consider the semaphore problem in a critical section problem solving, there is a semaphore known as mutex which is common to both wait and signal. Now, before entering the critical section, our process must invoke the wait mutex operation, and after it is completed its function on a critical section and exiting from there, it should operate this signal operation mutex on that particular object. But if we have some current scenarios that we will discuss now, then the mutex can provide a deadlock or in mutual exclusion cannot be completed its requirement. So we will now see various situations in this wait and signal mutex operations that are not provided with the concurrency control and process synchronization. Suppose that the process changes the order of wait mutex and signal mutex like this way. After performing this set of instructions, many processes can execute in their critical section as mutex is released and available for all the processes. Now, as all the processes are accessing the critical section simultaneously, then mutual exclusion is not satisfied. And it can be notified only if the processes are already executing in the critical section. But this scene is not always reproducible, and for this way the detecting error is probably impossible to detect. Now suppose that a signal mutex operation replaces with a wait mutex operation. Then what happens? In this situation, a process has gone the access permission for getting into the critical section, but after it's finished with its critical section, it cannot exit from the critical section as the next operation is also wait mutex. Here should be signal mutex, but it is replaced with a wait mutex function which put the system in the deadlock scenario. Now, if we omit any of the wait or signal mutex operation, then it will make the system in deadlock or either mutual exclusion is not satisfied. So, these three situations, semaphores can go in inaccurate way of the time error can happen. Now, this can be occurred by a genuine programming error or of an incooperative programmer's choice. Now these various types of errors handling during the semaphore using, we can introduce some high-level constructive alternates, that can be an example of a monitor. Now, a monitor is an abstract data type where the data variables are exclusive of the predefined functions that will be inside this ADT. Now, as they are already excluded from this function, these local variables can be included inside the monitor like this way. These variables can be included in the monitor like this way. Now the functions P1 or P2 are some program defined functions here which will act on the monitor, and the values of this variable state the state of the instances type. This type can be identified with the help of the programmer defined functions. And these functions only can allow to access these local variables, and these local variables with the formal parameters can access these functions as well. The monitor construct ensures that only one active process can there be in the monitor, and this code cannot be constructed using synchronization construction explicitly by the operating system, as it is already inherited by the monitor. Now, for this reason only, the variables that are local to the monitor can be accessible by only the functions of program defined which is already inside the monitor. Now, in this type of monitor, implications are not sufficient for some general purpose systems. For that, we need additional synchronization mechanism. One such mechanism can be adding some conditional construct. Now, a programmer who wants to make a tailor-made synchronization scheme for a monitor wants to declare some of the condition variables to it. It can be declared in this way. The only operation that can be invoked on these variables x and y of condition type are wait and signal. So any operation or process that want to gain access of the critical section must perform x.wait operation before accessing the critical section, and after exiting the critical section it should perform x.signal operation. The x.signal operation resumes the process that is suspended or busy waiting for that processes. Now, the signal operation is using a semaphore can affect the state of the operation also if there is no processes that are suspended and to be resumed. Now, in the x.signal does not make any effect to the state if there is no processes to be resumed afterwards. That is the main distinction between the monitor and the semaphore. Now suppose if P invokes the operation x.signal and Q also are there, that is need to be assumed, and this operation to execute its restart. Now this restart can be made on either P or Q. Now this restart can be made on either P or Q. Now, if the suspended process Q wants to resume, then calling process P must wait. Otherwise, if P continues its execution, then Q must wait. So there are mainly two possibilities, signal and wait and signal and continue. In signal and wait, P is continuing in the execution where Q must wait for signaling the other operation P or any other invocation. And in signal and continue, Q can continue execution while P must wait for some other operation or the signaling of Q. Now there are various reasons to choose among these two situations. If P is already executing in the situation of critical section, then signal and continue seems more reasonable than signal and wait. Whereas if P wants to halt and Q suspension resumes, then it should choose signal and wait operation. Now if we allow thread P to continue where Q is waiting for this operation, then maybe the time that Q is resumed, the logical condition for which Q was held may no longer be needed. So in this way, it should then signal and wait for queue to resume its execution. So the compromise between these choices and combinedly it was enhanced by a language of concurrent Pascal, where when P invokes a X dot signal operation, it immediately leaves the monitor and Q immediately resume the operation. Now in some languages known as C, C++, Java or she has used this monitor implementation to synchronize between the processes. And some languages known as Erlang has used some similar synchronization techniques but not exactly same as the monitor. So this is all for monitor and its usage. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.